So let's just use it as warm-up. Can anybody tell us how we can go about this? How we can evaluate this limit? So if people will join us late, they will at least join us on the integration aspect. So let's use this as a warm-up. So how do we tackle an integration, a limit question that looks like this? So I need ideas. Can somebody help us with, what they think? Anybody, please.
Um, can we take lane of both sides?
That is exactly what we're going to do. Well, before we take clean on both sides, let us try to understand why we have to start thinking of a way to, to go around. Why can't we just substitute directly? What would be the problem? So can you tell us what exactly would be the problem if we want to go directly, if we want to do direct substitution? What would be the problem?
I believe we will have 1 raised to power. Let me find out. Let me find. I don't know the value of cosec 0.
Okay, so if we do direct substitution, we're going to get this limit to be 1 plus sine 0 raised to power 2 times cosec of 0. And this is going to approach 1 raised to power infinity, because cosec 0 is 1 over cos 0. So as x approaches 0, this guy will go to infinity. So this is a problem. And when you have questions like this where it involves a power of x, and when you want to take limits, so the way to circumvent the problem of 1 to the power of infinity is to take limit of both sides. So we start by saying y is equal to the limit of this expression, 1 plus sine x to the power of 2 over sine x. So did I say cos? So it should be sine there, sorry, because that's the one that will go to infinity. 2 over sine x, and we take logarithm of both sides. So that means we're going to have natural log of y is equal to the natural log of the limit as x goes to 0 of 1 plus sine x 2 over sine x, or 2 cosec x. So like I told you guys yesterday, at any point in time, if you feel that what I'm saying you do not understand, do not let me go too far before you interrupt. You don't need to just raise your hand. Just go ahead and unmute your mic and interrupt me so that we can go over it again. So it doesn't make sense for us to both of us to be here. I should continue talking. At the end of the day, you don't understand stuff. So at any point in time, if I say something that you do not understand, you can just interrupt me and we can go over it again. Okay, good. So as I was saying, in this particular situation, we have natural log of y is equal to the limit as x goes to 0. So the logarithm can go inside. So the logarithm of 1 plus sine x, then raised to power 2 over sine x, or 2 cosec x. And the reason why we applied logarithm in the first place is for us to solve the problem of that power. So the logarithm, using the property of logarithm, log x to the power of n is equals to n log x, we can bring down the 2 over sine x. So this is equal to the limit as x goes to 0 of 2 over sine x, then 1 plus sine x. So ordinarily, I think for this question to make sense, it ought to actually be 0 from the right. Otherwise, there will be a technical problem. So when we look at this, it's actually just that solved itself, because I don't think there is going to, oh, I'm forgetting the logarithm. So this should be 2 over sine x, the natural log of 1 plus sine x. So like I said, it has solved itself, because eventually, so if we try direct substitution again, there will be a problem, because this part will go to infinity, because you're going to have 2 over sine 0. So this will go to 2 over sine 0, and that will go to positive infinity if you are going from the right of 0. So that is infinity. And when you plug in 0 here, you have natural log of 1. So this is infinity times 0, another indeterminate. So, and how do we work around infinity times 0 case? We rewrite the expression such that it gives us either 0 over 0 or infinity over infinity. And in this case, it just requires that so 0 plus, we write it as a fraction. So the natural log of 1 plus sine x over sine x. So can you see what I've done? I pulled out the 2 as a as a constant. Then I rewrote the expression as a fraction. So in this case, we can now, so if we check it direct substitution, it will give us natural log of 1 over sine 0, and that is 0 over 0. We are happy, because this means that we can now apply L'Hopital's rule. So applying L'Hopital's rule, this is equals to 2 times the limit as x goes to 0 of the derivative of natural log of 1 plus sine x over the derivative of cosine of x. And like we mentioned yesterday, the derivative of natural log of anything is simply the derivative of that thing over that thing. So that is f
Excuse me,
prime.
sir.
Yeah.
You said ddx of ln 1 plus sine x over ddx of cos
Of
x.
sine, it should be sine x. Thank you. My brain is working faster than my hands. Okay. Or should I say my hands is working? Well, they are just not in sync. So ddx of sine x. So the derivative of natural log of 1 plus sine x will be cosine of x over 1 plus sine x. So because the derivative of 1 plus sine x is cosine of x, then we're going to divide this by cos x. If we like, we can rearrange this, but if you don't have time for that, so just go ahead and substitute 0 for x. So this is cos 0 over 1 plus sine 0, everything divided by cos 0. And this is going to give us 2 times 1 over 1 plus 1, everything over 1. So basically, this is just equal to 2. And don't forget what is equal to 2. Where's the beginning of the chain of equalities? It is natural log of y. So it means we have natural log of y equals to 2. But it is not natural log of y that we are interested in. Our bone of contention is y. So in this case, it means that natural log of y is 2. Then we can take exponential of both sides. Take the exponential of both sides. So we have e to the natural log of y equals to e squared, which implies that y, that is the limit as x goes to 0 of, what was the question? 1 plus sine x over 2 cosec x is equal to e squared. Is it clear? Does anybody
Yes,
have?
sir.
Good, beautiful, beautiful. So, anointed, is it clear?
Yes, it is.
Beautiful. So the next warm-up question. So we've done one warm-up question in limits. So let's do another warm-up question. But this time around, let's do a warm-up question in application of derivatives. So the question here is saying find the, let me bring it up to the screen. Just a minute. All right. So the question says, where is it? Where is it? Come on. Yeah. Find the absolute extrema. Absolute extrema of this function q of x equal to 2 cos 2x plus 4 sine x. So what is the meaning of absolute extrema? So first and foremost, extrema is the general word for minimum or maximum. So it means the question is asking us to find minimum or maximum. And absolute is another word, in this case, for global. So we can find relative extrema and absolute extrema. Relative for local, while absolute for global. So how do we find extrema values? The first step is to find the critical points of the function. And what are critical points? Critical points or critical values, they are values of x for which the derivative is either 0 or undefined. So it means that the first thing we need to do here is to find the first derivative of q. And we set it equal to 0. Then we'll come back to discuss what it means to find the global one. So what is q prime of x here? So can somebody tell us what q prime of x is? Any volunteers? Can somebody tell us what q prime of x is?
Minus 4 sine 2x plus 4 cos x.
Thank you. Minus 4 sine 2x plus 4 cos x. This is the easy part. Now we go to the a little bit technical part. I'm not going to call it uneasy or difficult, or technical. So what do I mean by technical here? So we said critical point are the point for which q prime of x is either 0 or undefined. So we need to solve, we need to set this equal to 0 and solve for x. So if we set this equal to 0, to solve for x, I can divide through by 4. So that means I'll get cos x minus sine 2x is equal to 0. So does anybody have an idea of what I can do now if I need to solve this equation, if I want to get the values of x? What is the next step? What comes into your mind?
I think using trig identities.
Good. So which identity do you have in mind?
Sir,
Yeah.
can we say okay, it will know sine 2x
Yes, that is what I'm looking at.
will equal to 2 sine x cos x.
Beautiful. So we recall that sine 2x is equal to 2 sine x cos x. So it means that we can rewrite this equation as cos x minus 2 sine x cos x is equal to 0. So how does that help us? What next?
We'll factor out cos x.
Beautiful. So we'll factor out cos x. Cos x, then we'll have 1 minus 2 sine x equal to 0. What next? Oh, she's gone. Network is not kind to her today. So the next thing is to say, well, this is cos x equals to 0, or 1 minus 2 sine x equals to 0. And that means that cos x equals to 0, or sine x is equal to 1 over 2. I know you people did not really do trigonometry that much, but the trigonometry at this level is a little bit different from the trigonometry in the secondary school level. So ordinarily, you're supposed to be looking at general solutions of trigonometric equations. So when we say cos x is equal to 0, so there are infinitely many solutions, infinitely many. Okay, but at least from secondary school, we already know at least one of them or two of them. So what are the values of x that satisfies this? So x is either equal to pi over 2 or 3 pi over 2. As a matter of fact, any odd multiple of pi over 2 is a solution. Any integral odd multiple of pi over 2 is a solution. So it means that even negative pi over 2 or negative pi over 4,
Sorry, sir.
Yeah.
Please can you come back from the cos x equals 0 and sine x equals 1 over 2?
Yes. So I'm saying generally, any trigonometric equation, any trig equation has infinitely many solutions. And that is due to the periodic nature of trig functions. So it is not just one value or two values that will satisfy the equation. So if any x is a solution, X plus 2 pi is also a solution. X minus 2 pi is a solution. X plus any multiple of 2 pi is a solution. And like I said, from secondary school, SS1, you already know that if cos x is equal to 0, x is equal to 90 degrees. Or in calculus, because we deal with radians, that is pi over 2. But of course, it is not just pi over 2, even negative pi over 2. So this guy downstairs here is negative pi over 2. It is also 3 pi over 2. Okay, so if we continue to add 2 pi's to these two values, we are going to get solutions to this cos x equals to 0. So any odd multiple of pi over 2 is a solution to this. So x is equal to odd multiples of pi over 2, integral odd multiples. So that means pi over 2, negative pi over 2, 3 pi over 2, negative 3 pi over 2, and so on and so forth. But we need to be careful. What we are given is between negative pi over 2 and 5 pi over 4. So it means the ones that we are going to care about is negative pi over 2. So negative pi over 2, comma, pi over 2, comma. After pi over 2, which one follows? 3 pi over 2. So what is 3 pi over 2? 3 pi over 2, is it in the, let's check if it is in this region. What is 5 pi over 4? That is 5 times 45 degrees. What is 5 times 45? I think that should be 225, if I'm not mistaken. So this is pi over 4, pi over 4, pi over 4, pi over 4, then pi over 4. So that is 225 degrees. And what about 3 pi over 2? 3 pi over 2 is already here, so it is not in the range. So 3 pi over 2 is not here. So it is only negative pi over 2 and pi over 2. That is for cos x equals to 0. Then for sin x equals to 1 over 2, what x do you know that satisfies that from your SS1 knowledge? So if sin x is equals to 1 over 2, what x satisfies that?
30, sir.
30 degrees. But in calculus, you don't work with degrees. So what is that in radians? Terms of pi. So if 180 degrees is 1 pi, so what is 30?
It's not pi over 6 also.
It will be pi over 6.
Oh, I got it. Pi over 6.
Yeah, pi over 6. So that is pi over 6. But like I said, pi over 6 will not be the only one. There are infinitely many of them. There's something we call general solution. So if x is equal to pi over 6, which other one will be there? When you add 2 pi to pi over 6, it will also be a solution. When you subtract 2 pi from pi over 6, it will also be a solution. But in layman language, 30, you know 30 is a solution. You also know that 150 is a solution, right? So what is 150 in radians? So that is 5 pi over 6. Okay. So these are the critical points. So do you understand what I mean by 5 pi over 6 is a solution? So if you do 150, sine 150 is equal to 1 over 2. Sine 30 is 1 over 2. Then cos negative pi over 2 is 0. And cos pi over 2 is 0. So these are 4 critical points. So we want to find absolute extrema. So we have found extrema, the extremum points. These are not really the extrema. we have found the extremal point. So some of these represent minimum and some of them represent maximum. But when we say absolute extremum, we now want to look for out of these 4 candidates. So we now consider the 4 critical points and the end point of the interval we have. End point of the given interval. Okay, so the one that gives us the highest value is the absolute max, and the one that gives us the least value is the absolute mean. So what do I mean? You plug in each of them inside Q of X. So you will recall that Q of X is equal to 2 cos 2x plus 4 sine x. So when x is equal to negative pi over 2, so Q of negative pi over 2 will be 2 cos 2 times negative pi over 2 plus 4 sine pi over 2. And what will this give us? So 2 cancels 2. This is 2 cos pi plus 4 sine pi over 2. So you notice that I have swallowed the negative sign there. That is because the cosine function is an even function. So cosine of negative x is the same thing as cosine of x. And that is why cosine of negative pi is something as cosine of pi. And that will be 2 times negative 1 plus 4 times 1, which is equal to 2. We do the same thing. What are the endpoints? The endpoints of the interval. So thankfully, the endpoints are, negative pi over 2 is also a part of the endpoint. So the endpoints, negative pi over 2 and 5 pi over 4. So it means we only need to test 5 things. So we also do Q of pi over 2. Oh, I've made a mistake. So this should be 4 sine negative pi over 2. And that will be minus 4 sine pi over 2. This is minus 4. And this should be negative 2 minus 4. That is negative 6. So Q of pi over 2. So that one will be 2 cosine of 2 times pi over 2 plus 4 sine pi over 2. So 2 cancels 2. You are left with 2 cos pi plus 4 sine pi over 2. So cos pi again is negative 1. So this is negative 2. And sine pi over 2 is 1 plus 4, which is equal to 2. So 2 down, 3 to go. So what's the next one? Pi over 6, which is 30. So Q of pi over 6 is 2 cos 2 times pi over 6 plus 4 sine pi over 6. This is 2 cos pi over 3 plus 4 sine pi over 6. And cos pi over 3 should be 1 over 2. Sine pi over 6 should be root 3 over 2. So pi over 6 is 30, pi over 3 is 60. Sine 60. Oh, sine 30. What did before I want? Pi over 3 is 60. So cos 60 is 1 over 2. Yeah, that's correct. And sine pi over 6 is sine 30. That is also 1 over 2. Okay. So this is equal to 1 plus 2. And that is equal to 3. We are almost there. The next one is Q of, so we have done negative pi over 2, pi over 2, pi over 6. You're left with 5 pi over 6. That will be 2 cosine of 2 times 5 pi over 6. That's 10 pi over 6. Then plus 4 sine pi over 6. Let me remind you, at any point, if there's anything I'm writing that you do not understand, interrupt me and let me know. So this is equal to 2 times cosine of 300. Pi over 6 is 30, right? And pi over 6 times 10 is 30 times 10, which is 300. And that is the same thing as pi and cos 60. Cos 300 is something as cos 60. So that is same thing as pi over 3. 2 cosine of pi over 3 plus 4 sine pi over 6. So I think we've done that already. So that is actually 3. So you can actually check that. 2 times cos 100.
Sir,
Yeah.
I thought you were dealing with 5 pi over 6.
Yes. So it should be 4 sine
4 sine.
5 pi over 6. Thank you. So 4 sine 5 pi over 6 should be yeah, so it should also be 5 pi over 6 is 150. That's the same thing as sine 30. So that is plus, it's just the same thing. So it's just plus 4, and that is 3. Still, the answer is still going to be 3. Sine 5 pi over 6 is the same thing as sine pi over 6. Is that correct? Yes, I think it is. Yeah. So then the last one, Q of 5 pi over 4. This is the only one that would not want to go smoothly. But this is 2 cosine of 10 pi over 2, so which is just 5 pi. No, that's not correct. 5 pi over 2 plus 4 sine, come on, 4 sine 5 pi over 4. And any odd multiple of pi over 2, cosine of it is 0. So this is 2 times 0. You can confirm with a calculator. Cos 5 pi over 2, if we are in radians, cos 5 pi over 2, that should be 0. Then plus 4 sine 5 pi over 4. Sine 5 pi over 4 is negative of sine pi over 4. So that would be negative of root 2 over 2. Again, I hope I'm correct. Sine 5 pi over 4. That's correct. So this is equal to negative 2 root 2. So we now have all our values at the critical point. Which one is the smallest one?
2 2.
Are you sure?
No, 3.
This is the smallest one.
Minus 6.
Minus 2
Negative
root.
6.
Oh,
Negative 6 is the
negative 6
smallest
is there.
one.
Okay.
Because square root of 2 is less than 3. So negative 2 root 2 will be less than negative 6. So it means that is the absolute minimum within this interval. And what is the absolute maximum? The absolute maximum is 3, okay, gotten at pi over 6. So how do we write it? The absolute extrema are, so the first one is negative pi over 2 comma negative 6. So inside bracket, that is absolute mean. And pi over 6 comma 3. This is the absolute max. That's our answer. So let me go over it again quickly. The question says, find the absolute extrema of this function on the interval. So when you are given interval, that interval is for x. But when that absolute extrema is for the function itself, q of x. So you want to find the global maximum or global minimum within this interval for x. So the candidates for the x that will be the culprit, those ones are the critical points. So the first thing you are going to do is to find the critical points. And how do you find critical points? You take the derivative of the function, you set it equal to 0, and you find x. So that will involve most times quadratic equations, or some other times trigonometric equations. In this case, we have trigonometric equations. And for trigonometric equations, you have to be very careful with how you choose your solutions, because every trigonometric equation has infinitely many solutions. So since you people did not, 102 is not really peculiar about trigonometry, like, in the past, 121. So you need to try to recall your trigonometric identities and, look at general solutions when you are free. So when we did that, and we got 4 different values of x's that will satisfy this equation. You can, if you have time, you can actually plug in each of them one by one into this derivative and see if you get 0 or not. So having gotten that, any one of them that is not between negative pi over 2 and 5 pi over 4, we can throw it away. But the 4 of them here is between the given range. So those 4, together with the endpoint of the interval that we are given, will be the candidates for the absolute extrema. So to verify, you plug in all of them in the original function. The one that gives you the highest value is the absolute maximum, and the one that gives the least value is the absolute mean. Any question on that?
Sir.
Okay.
Concerning the critical point.
Yes.
I think you said values of x for which the q prime of x is either 0 or undefined.
Yes.
And the one you did is for 0.
Yes.
Yeah, can you explain the one for undefined?
Yes. So for functions that look like this, cos x and sine x, they are defined. What is the domain of those functions? Domain of those functions are negative infinity to infinity. So they are defined for all real numbers. So that is why I did not bother about undefined. But assuming one of our summands is sec x or cosec x or tan x or cot x or something like 1 over square root of x, all of these will have points where it is undefined. There was a question I gave out yesterday. Let me go back to it. The question I asked Inka to go and solve. So this particular question that I gave my students some weeks ago. So if f of x is equal to 6x plus 24 over x, if we are to find the critical point, so don't mind this other part. So for this question, I actually wanted them to only focus on the parts where f prime of x is 0. So for this one, you are going to consider both when it is 0 and when it is undefined. Because what is the derivative of f prime of x is 6 minus 24 over x squared. So to find the critical points, first and foremost, what value of x will make this undefined? So x equals to 0 is a critical point. Do you understand?
Yes, sir.
Because when you plug in 0 here, you get an undefined situation. Then the other critical point is gotten by setting this equal to 0 and solving for x. This means 6 is equals to 24 over x squared. Then it means x squared is equal to 4. It means x is equals to plus or minus 2. So the critical points for this function are x equals to plus 2, x equals to minus 2. This is where f prime of x is 0. While x equals to 0, this is where f prime of x is undefined. Do you understand?
Yes, sir.
So in the context of this particular question, the terms that we have are always going to be defined. There is no values of x where any of this is undefined because the domain of the sine and the cosine functions are all real numbers. Is that clear?
Yes, sir.
Beautiful. So that being said, any other question before we now start the real action of today? So today, my intention is for us to look at integration that would involve partial fraction and trigonometric substitutions. And before we are able to do that, let's take a very brief look at partial fractions. What's the idea of partial fractions? So this is a topic in the other mathematics course. So when I write something like 2x minus 1 over x squared plus 5x plus 6, is this a partial fraction? Can anybody tell me whether this is a partial fraction? Is this a partial fraction? Anybody?
Yes, sir.
This is not a partial fraction. This is a
Sir.
simple fraction. This is a simple fraction, but we can resolve this into partial fractions. So this is not a partial fraction, but we can resolve it into partial fraction. That is, we want to reverse the order of operations that we learned in GSS 2, GSS 3. In GSS 2, GS3, we learned something like 3 over x plus 2 minus 1 over x plus 3. So let me remove the numerator here. So how do we solve this one? We'll do LCM, x plus 2, x plus 3. Then this is 3x plus 3 minus x plus 2. So that will give us 3x plus 9 minus x minus 2. So this will give us 2x plus 7. So let me write this as 2x plus 7. So you see, this one here that we started from, this is the one that is actually the partial fractions. Okay, so this one that we got is the simple, compound fraction. So the process of going from here to here is resolving this compound fraction into these partial fractions. I hope that is clear now. So, and how do we do that? So before I continue, I need to tell you that there are actually 4 cases of partial fractions. We have case 1, the case where the denominator, so the cases are based mostly on the denominator. So when the denominator, we have linear non-repeated factors. Case 2, we have non-linear. So we are saying these are the type of denominators we have. Non-linear, non-repeated factors in the denominator. And case 3, we have repeated factors in the denominator. And the case 4 is when you have improper fractions in terms of the degrees of the numerator and the denominator. So what do you mean by linear non-repeated factors? So when your denominator is something like x minus a, x minus b, or let me say x minus p, x minus q, this is what we call linear, something that looks like ax plus b, that is linear. So the highest power of x is 1. And non-repeated means you don't have any power on them. So when you have this is already repeated. We have repeated that factor twice. We have repeated a linear factor twice. So when you have something like this in the denominator, that is case 1. And sometimes it will look like this. So you have to check whether you can actually factorize that expression. If you can factorize it, then you can break it down. Non-linear, non-repeated factors is when you have something like x squared plus 1 as one of the factors. So this is non-linear. It is a quadratic factor, and you cannot factorize it. Unlike if you have x squared minus 1. For x squared minus 1, you can break it down into x minus 1, x plus 1. But for x squared plus 1, you cannot decompose it. So for case 3, when you have repeated factors, and for case 4, when you have something on top whose degree is bigger than, so m is greater than n. So very quickly, let's look at, so let's say we want to integrate. So the main question now is integrate 2x plus 7 over x squared plus 5x plus 6 dx. So from what we did yesterday, I said immediately you see a quotient, when you see a fraction, the first thing that you come to your mind, well, can this be simplified? It cannot be simplified. You cannot split it up. Then the second thing is, can you use U substitution? Well, technically, if you are very good with manipulations, maybe you can think of a way to use U substitution here. But the ideal thing to take as U should be the denominator here. And when you take the derivative of the denominator, you are going to get 2x plus 5, which is not exactly what you have in the numerator. So U substitution is not advisable here. So what is that?
Yeah. So the denominator, it can actually be simplified if we try to use, like, what's it called? Like, there are two numbers that can multiply to give plus 6 and add to give plus 5.
So when I say simplify in quotes, what I mean is, so if you remember for what we did yesterday, so if you just have one term in the denominator, that's what I mean by simplify. So if you have just one term here and you have a couple of terms here, P of x, Q of x, R of x, such that you can now split this into P of x over F of x plus Q of x over F of x. That's what I mean by simplification. So but what you are saying is what we are actually going to use it here now. So we cannot use U substitution because the derivative of the denominator is not exactly related to the numerator. So the next thing will be using partial fraction. Okay, and to use partial fraction requires that because of what you said, because of this denominator can be decomposed into x plus 2, x plus 3, it means we can use partial fractions. And let us now do the partial fraction stuff on the side. So 2x plus 7 is equal to x plus 2, x plus 3. So when you have, I want to talk about partial fraction in case 1 now. So when you have this kind of partial fraction, you split it into, so for each of the linear factors, it carries a constant upstairs. So a plus the second one, so let me use 2 here. It doesn't matter which one comes first, but let's arrange it properly. X plus 3b. So we want to get the a and b that's, for which if we add this together, we are going to get this compound fraction. So in this case, how do we go back? So we can, of course, let's find the LCM. X plus 2, x plus 3. You can either say that or you say multiply through by x plus 2, x plus 3. So this is ax plus 3 plus bx plus 2. Then on both sides, this can cancel this. So we are left with 2x plus 7 is equivalent to ax plus 3 plus bx plus 2. So when we get to this stage, we can use different methods. One of them is the cover-up method, which is usually the easier one. But in some cases, it doesn't work. But the one that works generally is the comparing the coefficient method. So what do we mean by cover-up method? So we want to get a and b. So you think of what you will make as x. Why is this one here now? Come on, get away. So we want to look for what we put as x that will make this b vanish. So that is put x equals to -2. So you might be wondering, why did I not just write equal to here? And that is because we are saying it's not just an ordinary equation, because if it is an equation, only one value of x will work. So we are saying it is an equivalence, it is an identity. It means it is true. This line is true for all values of x. So that is why we have the liberty of saying put x equals to this, put x equals to that, for us to manipulate and get what we need. So put x equals to 2, that is to get a -2. So why do we know that will help us to get a? Because if I put -2 here, this whole place will vanish. So we have 2 into bracket -2 plus 7 is equal to a into bracket -2 plus 3 plus b into bracket 0. So this means -4 plus 7 is equal to a. So that means a is equal to 3. So the next one, to get b, so what should we use as x this time around to get b?
-3.
-3. Thank you. Does anybody want to ask a question? Is that person? Yeah.
Yes. Why exactly did we not make it -a? Since -2 plus 3 is equals to -1. Why is it not -a?
Are you sure -2 plus 3 is -1?
Yes, sir. Okay, it's
Minus. Okay. Are we on the same page now?
Yes, we are.
Okay. Don't worry, it happens. I understand. So put x equals to -3. So if x equals to -3, we have 2 times -3 plus 7 is equal to a times 0 plus b times -1. This is the one that will give us -1. So you have 7 minus 6, 1 is equal to -b. That means b equals to -1. So That means that our 2x plus 7 over x plus 2x plus 3 is equal to 3 over x plus 2 plus minus 1 over x plus 3. And let's see if that is exactly what we started with. That is exactly what we started with. So it means that this integrand is equal to 3 over x plus 2 minus 1 over x plus 3 dx. Which is now easy because we can actually just split this into 3 of the x over x plus 2 minus the x over x plus 3. And if we use substitution properly, this will give us 3 natural log of x plus 2 minus natural log of x plus 3 plus c. This is basically the answer, but if you want to move a step forward, this is exactly equals to natural log of x plus 2 cubed over x plus 3. I'm just applying the laws of logarithm. Nothing serious there. Is that clear? Are people still with me? Okay, good.
The last answer, I don't understand how done that with.
Okay, that playing around with laws of logarithm. So we know that I wrote something up there where, yeah, n log x is equals to log x to the power of n. So it means that 3 log x plus 2 is also equal to log x plus 2 cubed, right? Minus log x plus 3. Then we remember that log a minus log b is equal to log a over b. So if this is our a and this is our b, that is log x plus 2 cubed over x plus 3 plus c. So we can combine the absolute values. So x plus 2 cubed over x plus 3 plus c. Is it clear now?
Yes, sir.
Beautiful. Beautiful. So I remember at the beginning somebody said he or she had questions that require partial fraction. So before I
Yes, sir.
before I introduce my own. So yes, hold on, give me a minute. Okay, so do you have the question with you?
Yes. Should I write it out? Should I send it to you on WhatsApp, sir?
Oh, you can do that. Yeah. Okay. Beautiful. So let me see if I can bring it to the screen. Yeah, I got it. So we have the questions. I'm going to crop out the other parts and let's focus on one of them first. So number 3. So this is the question. Want to evaluate this guy. So let's forget about the limit first. Let's face the indefinite integral. X over x root x plus 1 dx. All right. So does anybody here have an idea of the direction to go? Anybody with an idea? Let's start from there. Anybody?
So how about doing use of substitution, Abby?
So what would you make as your u?
I don't know that one.
So you are correct in the sense that that is what we should start with. So you need to, but what is the the term that looks uglier the most here? It is a square root of x. So that should be a pointer for what we can make as our u. Okay? So
Yes, sir.
let u be equals to square root of x. So let's play around with this and see where it leads us. So this is when you want to do u substitution, remember the steps that I wrote out yesterday. After you have identified the u, the next thing is to take the derivative. So the u dx, what's the derivative of square root of x? It's just 1 over 2 root x. So that means dx is equal to 2u du, because that is 2 root x du. Right? And if u is equal to square root of x, what is x?
U squared.
U squared. Thank you. So we can now rewrite the expression. So the integrand will now become u squared over u squared times u plus 1, right? Times 2u du. So I hope people are following along. If there's any problem, you let me know. So is it clear up to this point? Good. Nice.
Yes, sir.
Beautiful. So this can be rewritten as u cubed over u cubed plus 1 du. Now, it is no more as ugly as it was before. Okay?
Yes, sir.
However, this is an improper fraction. It's, although it looks as if it's a proper one, but anytime the degree of the numerator is the same or greater than or equal to the degree of the denominator, then that's a proper fraction. We can either use long division like we did yesterday. You remember we did something like that yesterday? Or you just maneuver nicely with this. And how do we maneuver? So I'll do the long division as well, but if you want to maneuver, you can say this is u cubed plus 1 minus 1 over u cubed plus 1 du. You see what I'm trying to do there? I want to split this into u cubed plus 1 over u cubed plus 1 minus 1 over u cubed plus 1 du. If we were to use the long division, This will be u cubed in u cubed, 1. 1 times u cubed. We subtract, we get 1, right? So u cubed in u cubed 1, 1 times u cubed is u cubed. So it means that I think there is a problem here. We are not getting the same thing. We are supposed to get exactly the same thing. So the remainder is 1, which is not -1. Oh, sorry. Now I see what I've done wrong. So it should be u cubed plus 1 inside u cubed. We want to divide. What am I saying? We want to divide u cubed by u cubed plus 1. Primary 4 long division. So if we want to do 5 over 2, which one will be inside? 5 will be inside, 2 will be outside. So how do we do this? U cubed in u cubed 1. Then we say 1 times u cubed plus 1. So we get this, the minus, and we have -1. Now this is correct. So this is the quotient, and this is the remainder. And you remember that when you are breaking an improper fraction down, the answer will be quotient plus the remainder over the divisor. And that is why in this case we have 1, integral of 1 minus the remainder 1 over the divisor, u cubed plus 1 du. Any problem before we continue? Is this clear up to that point? So we can either have used the long division or just a simple manipulation. All right, so if that is clear, I'm going to move on. So this is now 2 of integral of 1 minus integral of 1 over u cubed plus 1. So that is A and B. The integral of A is just u, because integral of 1 is u. But consider B. Now that is where it becomes interesting. U cubed plus 1 du. How do we solve this? Does anybody have an idea? What can we do? Any idea? What can we do here? How do we integrate this? Anybody? All right, so that we don't waste time. So you see, the same way x squared plus 5x plus 6 can be broken down, this guy can also be broken down, u cubed plus 1. U cubed plus 1 can be factorized. As a matter of fact, any sum of 2 cubes can be factorized. So if we have a cubed plus b cubed, what does that give us? So generally, a cubed plus b cubed is equal to a plus b times a squared minus ab plus b squared. This is the sum of 2 cubes. In particular, x cubed plus 1, which is the same thing as x cubed plus 1 cubed, is equal to x plus 1 times x squared minus x plus 1. So you can verify that by expanding this. So if we expand this, so x times x squared, x cubed, x times negative x squared, x times 1 plus x, 1 plus x squared, 1 minus x, 1 plus 1, 1. So this cancels this cancels this. That is the sum of two cubes. If it were to be difference of two cubes, it's all similar. That is just x minus 1, x squared plus x plus 1. So why did we do all of that? Is to see that we can break this into 1 over u plus 1, then u squared plus u plus 1. So it just occurred to me that I did not say anything about the other cases of partial fractions. So we only talked about case 1. So what happens in case 2 is what we are going to see now. So the case 2 is when you have non-linear factor. So we have u plus 1, that is linear. So the partial fraction, let's come and do it by the side here. So 1 over u plus 1, u squared plus u, is it plus? It should be minus, sorry. U squared minus u plus 1. So the u plus 1 is the linear one. That will be A. But u squared minus u plus 1 is a quadratic factor that cannot be decomposed into two linear factors. It cannot be factorized. So if you want to confirm whether a quadratic equation can be factorized, do b squared minus 4ac. If you do b squared minus 4ac and you don't at least get a positive number, then it cannot be factorized. The best case scenario is for you to get a perfect square. If you do b squared minus 4ac and you get a perfect square, then it means you can factorize it nicely. If you get a real number that is not a perfect square, a rational number that is not a perfect square, it means it can be factorized, but you're not going to get nice numbers. You're not going to like the number you're going to get. And finally, if you get a negative number, that one cannot be factorized at all. So in this one, u squared minus u plus 1, if you do b squared minus 4ac, that is 1 minus 4, which is negative 3. So it cannot be factorized. So it is a non-linear factor. And how do we deal with non-linear factor? If you have a quadratic non-linear factor, then on top of it, you put a linear expression, bx plus c. If you have a cubic non-linear factor, on top of it, you put a quadratic expression, and so on and so forth. So just like when we had linear, we put a constant on it. But when we have quadratic factor, we'll put a linear expression on it. So just like we did the other time, again, the LCM shenanigans, a u squared minus u, why did I put plus c? Plus 1, then plus bx plus c times x plus 1. So why am I using u? So it should be u, not x. So bu plus c, then u plus 1 over u plus 1, u squared minus u plus 1. Then these cancel out as before. We now have 1 is equivalent to a times u squared minus u plus 1 plus bu plus c u plus 1. So we have seen how to use cover-up method, and I told you cover-up method will not work in all cases. So this is one of the cases where cover-up method will not work. I can actually use cover-up method to get A by saying let u be equals to negative 1. So that will cancel out all the B parts. But there is no value that I'm going to use on the A part that will help me to get B and C. So instead of using cover-up method, let's just go straight to the other method, which is comparing the coefficients. And to compare the coefficients, we would need to expand the expression that we have on the right-hand side. Okay, so if we expand that, we get AU squared minus AU plus A plus BU squared plus BU plus CU plus C. Are we still together?
Yes, sir.
Beautiful. So that means 1 is equal to A plus BU squared, this and this. Then plus B minus A plus CU. That is this, this, and this. Then finally, the constant plus A plus C. Now we can compare both sides. Since these two sides are equal, compare the coefficients and the constants. So comparing the coefficient of U squared, on the left, the coefficient is 0. On the right, it is A plus B. So we have A plus B is 0, equation 1. Comparing the coefficient of U, we have B minus A plus C is equal to 0 because there is no U on the left, equation 2. But from equation 1, we already know that B is negative A. So this means that negative 2A plus C equals to 0. So let's take that as our equation 2.
Sir, I didn't get that.
So from equation 1, from this one, B is equal to negative A. So if we put B as negative A here, we'll have negative A minus A plus C equals to 0.
Okay.
So that is negative 2A plus C equals to 0, which we can actually say C is equal to 2A. And for the constants, on the right-hand side, the constant is A plus C. On the left-hand side, the constant is 1. So A plus C is equals to 1, equation 3. But from equation 2, we already know that C is equals to 2A. So it means 3A equals to 1. Since C is 2A, that means A is equal to 1 over 3, and B is equal to negative 1 over 3, since B is negative A, and C is equal to 2 over 3, since C is 2A. I don't have the time, but ordinarily, one can check if that is correct. So put 1 over 3 here, put negative 1 over 3 here, and put 2 over 3 here, and solve it. You're going to get what you have on the left. However, that means that the integrand can be written as 1 over 3 u plus 1. So let me write out what the second part is. The second part is negative 1 over 3u plus 2 over 3 over u squared minus u plus 1. But if you take the LCM there, that is 2 minus u over 3 u squared minus u plus 1. Okay? Because this is negative u over 3 plus 2 over 3, LCM, that is negative u plus 2. That is 2 minus u over that. So I can write plus 2 minus u over 3 u squared minus u plus 1. Interesting. Du. I like this question because it's going to take us to many places. Okay, so we can factor out 1 over 3. So don't forget that this is just the B part of the question. Okay, so you have to keep reminding yourself. So this is 1 over 3 integral of 1 over u plus 1 du plus integral of 2 minus u over u squared minus u plus 1 du. Okay? Now I can split this one again into, so let's say this is, which I'm running out of letters. So let's say this is P and this is Q. P is soft, 1 over u plus 1 du. If you take appropriate u substitution, you will get this to be equals to natural log of u plus 1. But again, Q is another monster on its own. So how do we deal with that? So let's think about it carefully. Okay. So 2 minus u. 2 minus u. How do we work with that? Anybody has an idea? Let's write it out. So Q integral of 2 minus u, or minus u plus 2 if you want, over, so over u squared minus u plus 1. So does anybody on this call have an idea of what we need to do here? Yinka, you should know.
Sir, I would say we should do differentiate the denominator, but I don't know.
If you differentiate the denominator, you will get 2u minus 1, which is not a family of this. And we cannot factorize the denominator. So when you have something like this, so just listen. The reason why I called you Yinka is because you have done something like this recently. You've shown me something like this recently. So when you have a quadratic expression in the denominator that you cannot factorize, and its derivative is not a multiple or submultiple of the numerator, then you have to think of completing the square. Okay? So when assuming you can factorize it, you are going to use partial fraction. Assuming when you differentiate it, you get a multiple or submultiple of the numerator, you are going to use u substitution. But now that none of those work, we need to do completing the square. So this is one method that we've not seen. Okay, so how can I generalize it somewhere? I think I need to put it in a box. So anytime you have the integral of ax plus b, or let me say px plus q over ax squared plus bx plus c. So if ax squared plus bx plus c can be factorized as x minus rx minus s, you use partial fraction. If ax squared cannot be factorized, but has its derivative to be a multiple or submultiple of the numerator, then use u substitution. Otherwise, complete the square. So this will lead us to the last part of my agenda for today. So I like this question because it has shown us different angles of integration. So what do I mean by complete the square? Do you still remember completing the square that you did in SS2? So if you have, so if I have x squared plus 6x, and I ask you to complete the square, what are you going to add to it? Does anybody remember? What do we need to add to x squared plus 6x to make it a perfect square? Oh, yeah, SS2 mathematics, general mathematics, not for that maths. What do we add to x squared plus 6x to make it a perfect square? Okay.
Good.
We add 3 square.
Sorry, sir, I didn't get the question.
So when I say, what do you add? You see, this is an incomplete square. What do you call a perfect square? A perfect square is something that looks like this, x plus a squared. So when you have an incomplete square, when you have, I'm sure you've heard the word completing the square method. It comes from completing a square. So when you have this expression and you are told to complete it, it means you want to add something to it that would ensure that we can now write this thing as something squared. Oh, I have actually written it. So it is 9. But how did I get 9? So whatever you want to add to it will be the square of the half of the coefficient of x. That is what you add to something to make it a complete square. So, and that thing that you have added is what you put inside the parenthesis here. So x squared plus 6x plus 3 squared is equal to x plus 3 all squared. That is what we call completing the square. So if you now have, instead of x squared plus 3x, if you add x squared plus 6x plus 7, and you are told to rewrite these, complete a square. So what you're going to do is separate the plus 7 from it and do the addition that we did before, plus 3 squared. But because you are not doing magic, whatever you add, you must subtract it, minus 3 squared. So this is equal to x plus 3 squared plus 2. And that is the idea we would bring into this game. So we want to rewrite this in this, we call this the vertex form of any quadratic equation can be written in this form. Can be written in the form ax plus h squared plus k squared. So we want to rewrite this equation, this quadratic expression in this vertex form. So the way to do it is to do what I said here. So let me rewrite it. So u squared minus u, then you put the plus 1 here. Are you with me? Then, just like I added 3 squared and subtracted 3 squared, what do I need to add here? So it is the square of the half of the coefficient of u. The coefficient of u in this case is -1. So half of it is -1/2. Then you square that. So whatever you have added, you must subtract. So -1/4. So we added 1/4, we subtract 1/4. So it means that we can rewrite that as u minus 1 over 2. That minus 1 over 2 is coming from what we squared. Minus 1 over 2 squared. Then plus 3 over 4. Some people like to cram formula for this. I think the last time I saw Inga did it, she had a formula for it, but it is not my own thing. There are many things that you want to start cramming formula for you inside this little, although I have a very big head, don't tell anybody. But even with that, how many formula do I want to put in my head? So, but if you can actually, just go through the process, you see that it's not something too complicated. Any quadratic expression can be written in the vertex form. So for instance, if you have x squared plus, let me give you a simple one, x squared plus 10x minus 7. Why do I keep 7? Well, because 7 is a perfect number. Minus, let's say, minus 2. So how are we going to do this one? Again, you give them gap. Then you add the square of the half of the coefficient of 10. That is 5 squared. And whatever you add, you must subtract. Minus 25. So what will this be? This will be x plus 5 squared minus 27. So it's as simple as that. So that means this q will be equal to 2 minus u over u minus 1 over 2 squared plus 3 over 4 du. Are we still together?
Yes, sir.
Beautiful. Beautiful. And how do we do something like this? So what is the idea of changing it to that form? So from what we did yesterday, or what you might know, I'm sure you should know what, so first and foremost, this one, what is the answer to this one? What is the integral of 1 over x squared plus 1?
Tan inverse of
Tan inverse of x plus c. What if it is not 1? What if it is a squared? What is it going to be? What is it going to be? This is one of the things I wanted us to do today. So you have two options. It is either you cram what it is, or you can actually do the trig substitution. Because if you don't understand the idea behind this will be a little bit hard. Okay, it's okay. If nobody has the idea, let's come back here. Trig substitutions. Substitutions. So if you have integral of 1, I could actually just write out the formula. But let's see, if you have 1 over, so square root of x squared minus, is it x squared minus a squared or a squared minus x squared? Which one do I want to make first? Because some are more difficult than the others. So which one should I bring first? So let's see. I think I'm okay with seeing. Yeah, let's do a square minus x squared first. So Yinka,
Sir,
what are you saying? Yeah.
I'm trying to say that what if you manipulate it to in a way that you make it 1/1 plus x squared plus 1/1 plus x squared dx.
That is
But you
exactly the
understand?
idea. That is exactly what we are eventually going to do. And that is what is going to happen here as well. So I want to treat it in a general form first.
All right, sir.
So when you have 1 over square root of a squared minus x squared. So let me throw it open again. What is the integral of square root of 1 minus x squared? What is this? Again?
Sine inverse of
Sine inverse
x.
of x.
Yes, sine inverse of x. Okay. But when we see something like this, that is not just 1. So the traditional way of doing it, okay, I may not encourage you to do that in an exam that is not essay. If it is multiple choice, you don't need to go through all this. But this is how I do it. I don't cram stuff. I don't memorize stuff. So you do, because we want it to look like this eventually. You say, let x be equal to a sine theta. Okay? If x is equal to a sine theta, then it means x squared is equal to a squared sine squared theta. And dx d theta will be equal to a cos theta d theta. So, and we can now rewrite the integral to be equal to 1 over square root of a squared minus a squared sine square theta times a cos theta d theta. Are you with me? So this is the integral of a cos theta over square root of a squared into 1 minus sine square theta d theta. And this is equal to integral of a cos theta over absolute value of a square root of 1 minus sine square theta d theta. So in this case, we are treating the positive values of a. So this will just cancel out. And it is integral of cos theta over square root of cos square theta d theta. So this is also going to be equal to cos theta over cos theta d theta. And that will be equal to integral of the theta, which is equal to theta. But what is theta? You remember that x is equals to a sine theta. So sine theta is equal to x over a. So theta is equals to sine inverse of x over a. Right? Are we still together? I hope I have not lost you guys. All
No,
right,
sir.
good. So,
Yes, actually. But I cannot pinpoint where I was lost.
okay. So that's okay. Thanks for the honesty. So very quickly, when you have a squared minus x squared, the right substitution is x is equals to a sine theta. Then, because we know that 1 minus sine square theta will eventually give us cos square theta. So we do a sine theta. Even a cos theta will work anyway, but the best one is to use a sine theta. So when we have said x is equals to a sine theta, we need x squared, that is a squared sine square theta. Then dx is equals to a cos theta d theta. Are you okay with that? Such that we can rewrite this as 1 over square root of a squared minus x squared is this. A squared sine square theta. Then dx is a cos theta d theta. So I can factor out the a squared there. That was actually why we had to do a sine theta. So this would be square root of a squared 1 minus sine squared theta times a cos theta d theta. And this will be equal to, so this is the integral of a cos theta over square root of a squared cos squared theta d theta. Is this still clear? Yinka, I'm going over this because of you.
Sir.
Is this still clear?
Sir.
I didn't hear that.
I said yes, it is clear, sir. Thank you, sir.
Okay, good. So then the next thing will be square root of a squared cos squared theta is just equal to what? It's just equal to a cos theta, or in absolute value, but in this case, we don't care about that. A cos theta over a cos theta d theta. So this will be integral of the theta, which is theta. But from here, we know that x over a is sine theta. So theta from here. So theta is arc sine x over a. Right?
So I can't see what you're writing now.
A? Is that same for everybody? Can you see?
It's just updated now.
Okay. So theta is equals to arc sine x over a. So it means this is sine inverse of x over a plus c. That is the integral of 1 over a squared minus x squared. Okay? 1 over, so sine. So if we want to check if this is true, so how do we do it? We try to differentiate this. If we differentiate this, how do we differentiate this? So there are different ways to do it. You can use the chain rule. You can also say sine y equals to x over a. Then you say cos y dy dx is equal to 1 over a. Then okay. Then the y dx is equal to I think something is missing somewhere. Let me check. X is equal to a sine theta, dx is a cos theta d theta. Yes, a cos theta. We factor out an a squared. Yes. Then yes, that's correct. That's correct. Okay. So dy dx is equals to 1 over cos y times 1 over a. And because cos y is square root of 1 minus sine squared y, this will be square root of 1 minus x squared over a squared, which is square root of a squared minus x squared over a squared. And that would be square root of a squared minus x squared over a. So this is 1 over square root of a squared minus x squared over a times 1 over a. The a's cancel out, and we are left with 1 over square root of a squared minus x squared. So it means we are correct. So this is generally what happens when you have 1 over square root of a squared minus x squared. Well, without having to go through all of this, so the same way you know that 1 over square root of 1 minus x squared is this, you can also just add it to your repertoire, that the integral of, if it is not just a, if it's just one, if it's not 1, if it's a squared minus x squared, then the integral is sine inverse of x over a plus c. That is the point I've been trying to make sense. Is that clear?
Yes, sir.
Does anybody have any problem with that? So the integral of 1 over square root of x squared, a squared minus x squared is just sine inverse of x over a. That is straightforward. But for 1 over a squared plus x squared, what is it going to be? Does anybody know? The integral of 1 over a squared plus x squared.
Tan inverse of x over a plus c.
Yeah, that is almost correct. I think something is missing.
Right.
Okay.
I think something is missing. So let me just do it once and for all. We are already wasting time. 1 over a squared plus x squared. So how do we do this? We say, let x be equal to what? Let x be equal to a tan theta. So if x is equal to a tan theta, I'm just repeating almost the same process as before. A x squared will be equal to a squared tan squared theta, and dx will be equal to a sec squared theta d theta. Then we can rewrite this question as 1 over a squared plus a squared tan squared theta times a sec squared theta d theta. So this will be 1 over a squared into bracket 1 plus tan squared theta times a sec squared theta d theta. So one of the a will cancel one of the a's here. So we are going to be left with 1 over a. That is what you were missing, what you said. 1 over a of sec squared theta over 1 plus tan squared theta is also sec squared theta d theta. So this is 1 over a d theta. That is 1 over a times theta. So what is theta? If x is equals to a tan theta, then tan theta is equal to x over a, then theta is tan inverse of x over a. Can you still see my screen?
Yes, sir.
So this means that the integral is 1 over a. Like I said, that was what we're missing. Tan inverse of x over a plus c. Okay. So you should add that to your repertoire. Again, let's write. There are many of them. And because you may not have time to start doing all of this in the midst of a question, so it is good to have them in your toolbox. So the integral of 1 over 1 plus x squared dx, that one is tan inverse of just x. But if it is 1 over a squared plus x squared without square root, that will be 1 over a tan inverse of x over a. If you have 1 over square root of 1 minus x squared dx, that is just sine inverse of x. But if 1 is now a squared minus x squared, the answer is without a coefficient of 1 over a. Sine inverse of x over a. So at least if you don't remember anything, remember these 4 things from today, from today's class. So integral of 1, and I believe the only thing you are adding to your repertoire are just these 2 and 4. You already know 1 and 3. So how is it helpful for us here? So anytime you have something like 1 over square root of, so let's do a simple one, 4 plus x squared. If you have something like this, so what would be so there is no square root. If you have x squared plus 4 or 4 plus x squared. So according to what we just did here, in this number 2 fact, what would be the answer? Does anybody know?
1 over 2 tan inverse of 1 over 2.
X over 2, not 1 over 2. So 1 over 2 tan inverse of x over 2. You can see how simple it is. What if it is 1 over, I want somebody else to try it, x squared plus 5 dx. Anointed. What's it going to be? Anointed, are you still here at all?
Yes, I am.
So what is it going to be? Okay, let me help you. Let's change it to 25. So what's it going to be? Do you know what to do? Or should I explain what it is and I give you another one?
Yes, sir.
So x squared plus 25 is the same thing as x squared plus 5 squared. You agree to that, right? And if you look at what we are saying integral of 1 over x squared plus anything squared is 1 over that thing that is under the square tan inverse of x over that thing. So in this case, a is 5. So this is going to be 1 over 5 tan inverse of x over 5. Do you get it?
Yes, sir.
Now, let's come back to your own. So let me just give you a simple one then. What is 1 over x squared plus 9 dx? What's it going to be? Yeah.
That's
Time's down.
x square plus 3 square.
Yeah, so what is
So
the
that's
integral?
that's 1 over 3 tan inverse of x over 3.
X over 3. Favor, it's your time now. Then you have 1 over x squared plus 5 dx. What's it going to be? Favor. Is Favor with us? Favor, are you there? I think network is dealing with us seriously. So, Enoch or Joseph, can one of you tell us what it is? The integral of it.
1 over root 5 tan inverse x over root 5.
Good, thank you. Root 5. Good. So this is the main idea of what we want to do here. That's the main idea of what we want to do there. So when we have something like this, we know that we can actually rewrite it in a way that it looks like x squared plus a number. And we already know what to do when it is x squared plus a number. So if not that the original question is x, we could have just said, let x be equals to u minus 1 over 2. But since we cannot go back to x, we can use another number. So let v be equals to u minus 1 over 2. such that the v, the u, the v is just the u because it's just one. So we can rewrite the equation to be, so if v is u minus 1 over 2, it means u is equals to v minus, v plus 1 over 2. Like I said, if you don't understand anything I'm saying, you stop me at any time. So this is 2 minus v plus 1 over 2 over v squared plus 3 over 4 dv. And this is exactly equal to v, let's say this is, what is 2 minus 1 over 2? That is 3 over 2 minus v over v squared plus 3 over 4 dv. Interesting. At this point, we can break things down. So this is the same thing as 3 over 2 over v squared plus 3 over 4 dv minus v over v squared plus 3 over 4 dv. Is anybody lost along the way? Olayinka, are you still with us? Is it clear up to that point?
Yes, sir, it is.
No, sir.
So give me a minute. Hello. Good afternoon. Please, can you give me 30 minutes? I'm teaching a class right now, so I'll be done. Oh, beautiful. All right, you're welcome. Okay, so let's continue. So as I was saying, okay, so somebody said doesn't understand where we are, right? So which part is unclear? Was it Joseph or Innocent? Which part is unclear?
From the 3 over 2 minus v over v squared plus 3 over 4.
Okay, so let me clean this step. So what we have here, come on, is, so this is 2 minus v minus 1 over 2, and 2 minus 1 over 2 is 3 over 2. So I can write that as 3 over 2 minus v over the denominator remains the same, v squared plus 3 over 4. Then I want to split it because that is when it is easier to do. Split it, when we have a plus b over c, I can always split it as a over c plus b over c. So this is 3 over 2 over v squared plus 3 over 4 dv. Then the second one, minus v over v squared plus 3 over 4 dv. Is it clear now up to that point, Joseph? Good. So the first part can be written as 3 over 2. I can bring the 3 over 2 out. Integral of 1 over v squared plus root 3 over 2 squared dv. Why did I write it that way? So that you can recognize the side play we did here. So it's just like 1 over x squared plus something squared. So root 3 over 2 squared dv. And the other one is just v over v squared plus 3 over 4 dv. So I believe you should be able to tell me what the left-hand side will be, from what we learned on this side. So Eva, what is it going to be? So there'll be 3 over 2 of what?
Um, 1 over
1
1
over
over
root 3 over 2, right?
yes, 1 over root 3 over 2.
And that is actually 2 over root 3.
Yeah.
Then
Times
tan inverse
um,
of 2x over root 3. It's supposed to be tan inverse of x over root 3 over 2. Right?
yes, sir.
Good.
Yes, sir.
So 2 can cancel 2. So we have 3 over root 3 there. The other side, we cannot use that same thing because what is on top is not 1. But it's a simple question because we can use u substitution there. Okay? So if you're not supposed to use u again, but let me say u bar is v squared plus 3 over 4, then it means the u bar dv is equals to 2v, right? So how do I know I can use u substitution? Because I know that if I differentiate that denominator, I'm going to get a multiple of the numerator. That is the secret ingredient for u substitution. So it means that the v is equals to the u bar over 2v. So I can write this as v over u bar times the u bar over 2v, such that v cancels v. So we are going to get 3 over root 3 tan inverse of 2x over root 3 minus 1 over 2 integral of 1 over u bar du bar. Like I said, I like this question that Eva has brought to us because it's going to show us a lot of different things. So, Jepos, do you have anything to say?
Yes, sir.
So, what is it?
This last part you wrote is somewhat confusing.
Okay. So do you understand up to this point?
Yes, sir, I do, sir.
Good. Then we want to focus on this. So let's write it somewhere else. So if I have integral of x over x squared plus 3 over 4. This is if this is the ordinary question, what should you think of? The thing you should think of here is u substitution, because when you take u as a denominator, if you differentiate that, you are going to get a multiple of x. So this is going to be, so if you say u is equals to x squared, then it means the u is equal to 2x dx, and it means the x is equals to the u over 2x. So I can write this as x over u times the u over 2x. So x cancels x. We are left with 1 over 2 integral of 1 over u du. That's exactly what I did there. Is that clear?
Yes, sir.
But this time around, x is actually v. And I don't want to use u again. Or let's just assume we don't know what u is before. So let's say u equals to, well, we are not supposed to use u again because we have already used u somewhere there. By the time we start back substituting, so that we don't get confused. So let's use w instead of u bar. W equals to v squared plus 3 over 4. So the w dv is equal to 2v. Then it means that the v is equal to the w over 2v. So this is v over w times dw over 2v, such that v cancels v. So this will be 3 over root 3 tan inverse of 2x over root 3 minus 1 over 2, 1 over w dw. And finally, that is 3 over root 3 tan inverse of 2x over root 3 minus 1 over 2 ln W plus C. We will now start a series of back substitution. So we start with W because everything must be in terms of X. So this is 3 over square root of 3 tan inverse of, this should be V, not X. So 2V, 2V, 2V. So 2V over square root of 3 minus half natural log of, what is W? V squared plus 3 over 4 plus C. So we have gone from W to V. We need to go back from V to what gave us V? V to U. So that is 2 over 3 tan inverse of, what is U? U is, V is U minus 1 over 2. That is 2U minus 1 over 2. So if V is 2U minus 1 over 2, so this will be 2 times 2U minus 1 over 2 over square root of 3 minus half
Sorry.
natural, yeah,
So,
yeah.
how did you get 2 over 3 tan inverse of this particular line you're doing? How is
Oh,
it
it
2
should be,
over 3?
it should be 3 over root 3. Thank you. Then natural log of V squared, V again is 2U minus 1 over 2 squared plus 3 over 4 plus C. So that is 3 over root 3 tan inverse of 2U minus 1 over root 3 minus 1 over 2 natural log of, should I square that? Should I not? So that would be 2U minus 1 squared plus 3 all over 4 plus C. So this is the answer to the one that involves U. So this is the answer to this integration of Q. Okay? So this is Q, the one that has U. So where did Q come in? Q came in from here. Okay, so we need to bring it back into this place. So we want to do 1 over 3 into bracket P plus Q. So we want to do, so 1 over 3 P plus Q will be equal to 1 over 3. What is P? Uh-oh, I've jumped a page. So it should be here instead. So 1 over 3 P plus Q should be 1 over 3. Where is P? P is this guy, natural log of U plus 1, plus what is Q? This guy. So instead of rewriting it, I have the advantage of using the digital material. I can copy, I can paste, and I'll close the bracket. So what is equal to this? Let's trace it back. This is just the B part. So we still have 2 times A minus B. So we want to do 2 times A minus B. So this is B. And what is A? A is just U. A is the integral of du. So A is just U. So this is 2, so let me leave space. 2 times U minus the whole of B is copy, paste. So actually, I can multiply through by that 3, 1 over 3 outside. So it means we can have 1 over 3, then the 3 here will go away, then we'll have 1 over 6 here. So what is this 2 times A minus B? Let's trace it back again. This 2 times A minus B is actually, the I itself. It's actually what we are looking for. So there is only one more substitution we have to take back. U is equal to square root of X, and we'll be done. So it means I now is equal to, I think I should copy. Ever, you see what you have made us go through. So I is equals to 2 root, but I like that I like this kind of question because it helps you to see, it touches many different parts of integration. So 2 root X minus 1 over 3 natural log of root X plus 1 plus these 2 root X, then this one 2 root X minus 1 squared plus 3 all over 4 plus C. What a question. So look at how innocent the question is. So not our ever innocent. Look at how innocent the question is. Where is it? Oh, we are not even done. We have only done the indefinite integral. So you still need to
1 and 0.
You still need to do 1 and 0. So it means, so integral of I from 0 to 1 dx will now be, so you plug in 1, that will be 2 minus 1 over 3 natural log of 2 plus 1 over root 3 tan inverse of 2 minus 1, 1 over root 3 minus 1 over 6 natural log of 2 minus 1 is 1. 1 plus 3 is 4. 4 over 4, that is natural log of 1. So this is for the 1. For the 0, that would be 0 minus 1 over 3 natural log of 1, because 0 plus 1 is 1, plus 1 over root 3 tan inverse of negative 1 over root 3 minus 1 over 6 natural log of 1. Because when you plug in 0 here, you have minus 1 square, 1 plus 3, 4, 4 over 4, 1. Oh, the beauty of it, natural log of 1 is 0. So this can go, this can go, this can go. So we are left with equals to, this is so annoying because the answer will now be something very simple. So this is equal to 2 minus 1 over 3 ln 2 plus 1 over root 3 tan inverse of 1 over root 3 minus 1 over 3 tan inverse of negative 1 over root 3. What is tan inverse of 1 over root 3? That should be pi over, and what is 1 over root 3? That is tan 30. So that's pi over 6. So this is 2 minus 1 over 3 natural log of 2 plus pi over 6 root 3 minus, what is tan inverse of negative
Won't
1
they just subtract each other out?
What did you say?
I said, won't they just subtract each other out? This 1 over root 3, tan inverse of 1 over root
Tan
3.
inverse, not necessarily, because tan inverse of negative x is not just equal to minus tan inverse of
Yes,
of x. Okay, it's not necessary. Sometimes it is, but there are conditions for which it doesn't happen. Okay.
Okay.
So let me just confirm in this particular case. So in this particular case, it does. Okay, so we are going to, it is not going to even cancel out because this one is negative. So yeah, so it will be plus pi over 6 root 3. So our answer will be 2 minus 1 over 3 natural log of 2 plus pi over 3 root 3. This is the final answer of that question. And I think it is a very good place to stop for today because we have absorbed a lot of new material. Okay, so I actually had some other things lined up before, but I think this is enough. If you can take your time to go over the things that we have discussed here. So the partial fraction stuff we talked about, we only saw the case 1 and case 2 even. Okay, so case 3 and case 4. Okay, I think we saw a little bit of case 4. We saw case 4 because we divided here. Yes, this is case 4. So when you have to divide, long division, that is case 4. Then case 3 is the only one we've not seen. So maybe the next time we meet, we'll look at a question that has case 3 and some other trigonometric substitution questions. Any other question before I before I end the call? Olayinka, are you still awake today?
Jesus, yes, sir.
You now elongated, and you don't even know that the recording did not stop yesterday because you were still on the call. Because when I was trying to break it up, I saw that it was 4 hours long, and I realized that it was only Olayinka after 2 hours, 13 minutes. But it's okay, it's all good. So I hope you guys have learned something today so that we've not wasted time together. Yeah.
Yes, sir.
Sir, please.
Yes, sir.
I hope we can be giving this kind of question for our test or even exam.
I actually cannot say yes or no. I don't know the mind of your lecturer. But I don't think I don't think something like that would if it if left to me, I don't think something like that would. But it is good for you to be confident in doing something like this. And it won't be as long as this if you already know some of the things that I have tried to elaborate. Some of the things that can be shortened here. Okay. But this is too long for a test question. It is not something I would give my student, even for an exam. Unless this is the only question or I have just 2 questions for the exam. Okay, but this is a good question that I like because it covers a lot of things. Any question before we call it a night? All right, so I believe there is no other question. So you guys should have a good night rest and we'll see another time. I will send this PDF to those I have on my contact list, and I'll also, when the video is ready, I'll also send a link out. Have a good night.
Thank you, sir.
Thank you, sir.
Yeah, you're welcome. Okay.